Now we're going to talk about limits at infinity. And these are not to be confused with what we just talked about. So up to this point, every time we've taken a limit, we've let x approach some number a, and we've approached, either from one side or the other or both. Now what we're going to do is we're going to let x approach infinity or negative infinity. So infinity is not a number, it's an idea, right? This idea that x is going to go to infinity means that x is growing and growing and growing without bound. X going to negative infinity means it's growing but negative, but getting bigger and bigger and bigger. So it's impossible to do a limit from both sides, because when you go to infinity, there is no other side of infinity. So it's just more of the idea that this number is getting huge. So this is the notation for it. All we do is we say x is either going to go to infinity in the limit, or x is going to go to negative infinity. So we'll take a look at our first example of this, and we go back and look at this one function this function just has so many nice properties to it. F of x equals 1 over x, right? We already know what the graph looked like as we did this, right? As we approached 0, we knew what happened. But what about this? What's the limit as x goes to infinity of 1 over x? So let's do it. Let's talk about it. What's happening on the top? Where's it going? 1, right? That's just staying 1. So would you all agree that the numerator is fixed? And it's positive? Yeah? And then on the bottom, where's it going? To infinity, right? So it's getting bigger and bigger and bigger and bigger, right? This is headed to infinity. So let's actually think about, if we have our calculators, we can just start picking numbers. If we go, let's say, to 100, right? 1 over 100 would be 0.01, right? But, 100 is not infinity. Infinity means keep going, right? So let's, instead of going to 100, let's go to, 1,000. 1 over 1,000, that'd be 0.01, right? And what's happening to those numbers? The further out we go, right? Sorry. 0. So these numbers are doing what? So the further out we go, the smaller it gets. So we have a fixed number on top, and the denominator is getting big. That ratio gets small. It's the opposite of what just happened, isn't it? Before we were saying if it's fixed and the bottom goes to 0, then it gets huge. Here we're saying fixed over big gets small. So this should head to 0, shouldn't it? This should head to 0. Now, does it matter whether or not it's positive or negative? What do y'all think? If I take a negative number and divide it by a huge number, is it still going to be really, 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 really small? Is it still getting close to 0? Now, it might be very small negative numbers, might be very small positive numbers, but 0 is 0. Is 0 positive or negative? Neither. 0 is neither positive nor negative. So when you're headed to 0, it really doesn't matter what sign you have on top. So on your sheets, with the boxes, right? Y'all see that? I think it's the bottom right-hand corner. Fixed over, and see how it says fixed, positive or negative. Doesn't matter what the top's doing. If you got something on top that's fixed, bless you, over something on the bottom that's getting infinitely, that's enough. There's something that's getting bigger on the bottom, right? And it does not matter if this is positive or negative or this is positive or negative. The ratio is going to get small and approach 0. Nice, right? So let's do an example like this. How about limit x approaches infinity? And let's do, now we'll keep it simple still, 5 over x to the 3rd power. I take a look at that, I go, okay, where's the numerator headed? It's a fixed positive number, right? Over, the bottom is headed to, well, infinity, right? Infinity cubed. What do you think about infinity cubed? It's still infinitely big, right? It's a huge number. It's just even huger. Huger? More huger. It's big, right? Infinity, right? Fixed over infinity goes to 0, you're done. There's nothing else to do. If I do this, limit x goes to negative infinity of the same problem, does it change anything? No, because the top is still headed to 5. The bottom is headed to negative infinity, but that doesn't change anything. Fixed positive over infinite but negative has no impact on the fact that this is still headed to 0. This was like your horizontal asymptote in college algebra, right? When you go out to the right, it flattens out. Go out to the left, it flattens out. Same concept. It doesn't have it? Where? It doesn't say? Oh, go ahead and put positive or negative there. Should be positive or negative. It doesn't, yeah. On the boxes on the bottom infinity can be plus or minus. Thank you for pointing that out.
So this is a horizontal asymptote?
This would be a horizontal asymptote, yep. Now, I'm not going to test y'all on that. I'm just pointing it out. All right, good? So these are real easy, aren't they? I mean, not really. I mean, the problems I've given you is pretty simple. You just fixed over infinity, done. All right, so I want us to think about this. What would the limit be as x goes to infinity of x cubed minus x? All right, so let's talk about where things are going. X goes to infinity. What does infinity cubed go to? Big, right? Infinity. So this is headed to infinity minus what? Something that's infinitely big as well. What do you think? Do you think that's 0?
Negative.
Is it negative infinity? What do you think? All this infinity means is what? That's getting really big, right? And all that infinity means is that's getting really big. Does that mean they're getting big at the same rate? No. Do you all agree that this would be getting big a lot faster than this would be getting big?
Yes.
You think about if you plugged in the number, I don't know, 10, that'd be 1,000 minus 10. If you plugged in a million cubed minus a million, this one is winning, isn't it? This one's getting a lot bigger, a lot faster than that one. So the way we can actually see what's really happening here, other than just deducing it logically, is that we could see that there was a GCF there. We could have pulled an X out of both of those, right? Couldn't we have pulled an X out of both? And then if you look at it this way, now you have multiplication, don't you? See, if I tell you right now, I've got a big number minus a big number, you can't tell me what that is, right? Big minus big. Remember, infinity is not a number, it's an idea. So big number minus big, no idea. But if I factor out, now what I have is what? Big number, right, times what's happening in here. Big number squared, take away 1. Still big number, right? Now, if I tell you I have a big number times a big number, you'll tell me the answer is what? Big number, right? See, big minus big, you can't tell me. Big times big, you can say, yes, that's big. So this would be infinity. So let me just back up and just go through this again. The reason the answer to this is infinity is because the x cubed dominates the x. It's a higher power, and so it overwhelms this x. If I change the problem around and I do this, x minus x cubed, now this is the one that's dominating, right? So this is huge, infinity. Taking away infinity, I don't know what that is. It seems like this one should win. Pull a GCF. Now run your limit again. This becomes huge, infinity. times, now this one is 1 take away a big number, right? What's 1 take away a big number? It's negative though, right? That's a negative big number. So now you've got a big number times a huge negative number, and a positive times a negative will be negative, and it'll be huge. Y'all follow me? It's like a number sense, right? We're trying to get a sense of what's happening as these values of x get big. Generally speaking, if you ever have infinity minus infinity in a limit, you're going to need to do some algebra to figure out what's going on. That's on your sheet. Top left box. Remember how we had 0 over 0 there? And it said 0 over 0 algebra trick. Do you see in there it says infinity minus infinity? Do you see? That means that we have to do some algebra, some trick. That's what we just did here. All right, I'm about to proceed into some more examples. I want everyone to understand that this right here, the factoring we did, I'm going to skip that step as I move forward. I'm just going to deduce this logically. That overwhelms that, so this is positive. If I had this problem, I would say that overwhelms that, so the answer is negative. Understand? I'm not going to go through all this work of factoring again. So let's now do a new problem, something we have not seen. Limit x goes to infinity. Let's go let's go 3x squared plus 1 over, let's go with x to the 4th plus 9. 9x. How about that? Take a look at it. What's happening up top? Where are we headed? Infinity squared is infinity times 3 is infinity plus 1 is still infinity. That's a huge number up top, right? We're headed to a huge number. And we're dividing that by what? A huge number plus 9 times a huge number, that's still a huge number, right? This is infinitely big on the bottom as well. Infinity over infinity. What happens when you take 4 and divide it by 4? You get 1. 10 over 10, 1. Infinity over infinity is not 1. Because, again, this is an idea. We're saying that this is a huge thing divided by a huge thing. Do not ever look at infinity as a number. So this right now, I don't know the answer. I do not know I know it's positive, right? If I have an answer, it's a positive number because I have positive over positive. But do you see in your box where we had 0 over 0? Do you see next to it we have infinity over infinity? What do we have to do? Algebra, some trick. Okay, here comes the algebra, the trick for this. There's a standard procedure when you see infinity over infinity. There's a standard thing that you want to try, all right? So here's what it is. What we're do I want to give you the motivation first, or do I want to just do it and then, I'll do it first, then I'll show you why we did it. Okay, the standard procedure is to do this. Whenever you see infinity over infinity, you look at the denominator. Okay, you look at the denominator and you look for the highest power of x that you see. X to the 4th, right? What I'm going to do is I'm going to try and turn that into a constant. I'm going to try and make it turn into a number. Well, how in the world am I going to do that? To turn x to the 4th into a number, what I'm going to do is I'm going to multiply it by 1 over x to the 4th. See, if you take x to the 4th and multiply by 1 over x to the 4th, what does that turn into? 1, right? 1, right? They just cancel, you just get a 1. I want to turn it into a 1, and I'll discuss why after I finish the problem, and hopefully it'll make more sense when I'm done. So I need to turn that into a 1, so I'm going to multiply it by this. Now, if I do that, I have to multiply it out here in front. What I do to the bottom, I have to do to the top. I can't just arbitrarily multiply the bottom by 1 over x to the 4th. So I'm going to do this on my next line. Limit x goes to infinity Okay, up top, I do 1 over x to the 4th. And on the bottom, I do 1 over x to the 4th. And I'm sticking that in front of what I had, which was 3x squared plus 1 over x to the 4th plus 9x. The reason I'm doing this again is because I wanted to turn this right here into a number. I'll revisit why in a moment, but let's see if we've achieved that. Let's multiply this through the bottom first. We're going to go here, and we're going to go here. I'll do the top as well, but let me just pause on that for a moment. So on the bottom, when you multiply this times this, what do we get? 1. Okay, plus, now this one times this one. Yeah, when you go here to here, you're going to have 9x on top, on the bottom x to the 4th. So one of the x's cancels, right? And so you just get 9 over x cubed. Y'all agree? So you get 9 over x cubed. Let's see what happens up top. When I do here to here, what do I get? 3x squared over x to the 4th, right? That's what I get when I multiply here to here. Cancel out 2 factors of x, so we get 3 over x squared. And then plus, and then here to here, well, 1 times that is just itself. You doing okay? Do you want to help me finish this? No, not you. What's your name? I'm sorry? Enrique, are you all right? Tired? Okay. I'm just more worried about your success in the class. So when you're sleeping, it's hard. Unless you understand it, then that's a different story. So that's why I'm allowing you to. Have you seen something like this before? No? Okay. All right. Everyone understand what I've done? Okay. Why did I do that? What's going to happen on the next step? If I actually take the limit and let x go to infinity, what's going to happen to everything almost? As x goes to infinity, what does this become? Fixed over infinity. What does fixed over infinity go to? 0. What is this? Fixed over infinity. That goes to 0. What is this? Fixed over infinity. That goes to 0, right? What about this one? It doesn't go to 0, right? And that's by design. I made it that way, right? Remember I said pick the highest power here and make that turn into a constant. If this is the highest power, then would you agree that that one is going to go to 0? See, because the power here is higher than that one. So when I divide through by x to the 4th, that'll turn to a constant. That'll turn into a number over x to some power. That's going to go to 0. What I'm guaranteeing myself is that when I take this limit, my denominator is not going to 0. It's going to a number.
So it has to be the highest power
Has to be the highest power.
in the denominator.
In the denominator only. Okay? So let's now continue. Let's now continue. Let's go ahead and take the limit, so I'm no longer going to write the limit. We said this goes to 0. That goes to 0. That goes to 0. We say, in math, we like to say that those vanish. Okay? They vanish. They go away. As x gets bigger, they get smaller. They essentially go to nothing. And now on top, I'm left with 0 plus 0, which is 0. And on the bottom, 1 plus 0, which is 1. And 0 divided by 1 is 0. So our answer is 0. So when you look at this ratio, x was going to infinity, the top was getting huge, the bottom was getting huge, but at the end of the day, the denominator was much more powerful than the numerator because of the x to the 4th. And so this got so big so fast, it basically squashed this ratio down to nothing. So the rule of thumb again is when you have infinity over infinity, you look at the denominator, you go find the highest power, and then what you do is you come in with 1 over that power on the top and bottom. Let's do another one. I'm going to let you do this one. So how about 4x cubed plus x plus 1 over x cubed minus 3x, and that's it. And as a quick little, before you get too deep into this, just look at the denominator right now. Who wins this battle? If x is going to infinity, who wins, the x cubed or the 3x? X cubed, right? So this is infinity cubed minus infinity. This is headed to infinity because that one dominates that one. So right now what you have is infinity over infinity. And what did I say when you have infinity over infinity? You do it, okay? I'll be back. So see if you can work it out. Talk with your neighbor. Check your answer with your neighbor. You have a question? I'm going to start working it out up here. So you should be coming in with 1 over x cubed over 1 over x cubed. How many of you got that? That part right there? Yes? Anyone need help on that? Anyone have a question? I'm doing the cancellation of the x's in my head. So like when I'm doing this to this, the x cubes cancel. When I go here to here, I cancel one of the x's. So by design, right, by design, by the method of coming in with the highest power of x on the bottom, I'm guaranteed that I'm going to have just a number here, right? Every time. Whatever else happens, happens, right? So when I take this limit now, this one goes to 0, this one goes to 0, and that one goes to 0, right? What do I still have up top? 4, and on the bottom, 1. 4 over 1, your answer is 4. So remember, this represents a horizontal asymptote, right? As you go out on this function that way, it's where the function is headed. It's headed to 4. As x gets bigger, the function goes to 4. Yes?
Why does it go to 0?
Because you have up top a fixed number, right? And then the bottom is getting huge. Anytime you have a fixed number over a huge number, it gets really, really small. Okay, so some of you may recognize this from college algebra. I know at least one student got the answer very quickly, because in college algebra, if you're studying this function in college algebra, you call this a rational function. Rational functions. Remember doing rational functions in college algebra? They sucked. You had to get like, vertical asymptotes, horizontal asymptotes. You had to figure out x-intercepts. It was a mess, right? And you were taught in college algebra, well, depending on how you were taught, that if you're trying to find the horizontal asymptote, then all you have to do is look at the degree of the numerator and denominator. And if those degrees are the same, then you would just take the number here and the number here and divide them, and that would be your horizontal asymptote, right? Do you remember seeing that in college algebra? Why does that work? If these powers are the same, right? If they're the same powers, then if I use this method, won't this number be here and that number as well? Because they were the same powers, weren't they? So when I come through with 1 over x cubed, 1 over x cubed, that goes away, I'm left with the 4, I'm left with the 1. And as long as these two powers are the same powers, that would happen every time. So those two coefficients would always be what's left. Yeah? Okay. So now, why don't we just do that then, right? Why go through all the work? Well, because not every function that we see in calculus is rational. It's not a rational function. So let's do this one. Limit x goes to infinity of how about 5x plus 1 over the square root of 4x squared plus x. All right, this one, you cannot use that method that you learned in college algebra because this is not a rational function. A rational function is a polynomial divided by a polynomial. That's a polynomial. That's not. That's a square root function or a radical function. So you can't use the method from college algebra. So you need something else. Let's just check to make sure that when we let x go to infinity, we get infinity over infinity. Do we? 5 times infinity, infinity, plus 1, still infinity. Okay, on the bottom, 4 times infinity squared is infinity, plus infinity is infinity. Oh, the square root of infinity gets a little smaller, but who cares, right? Still infinitely big. Infinity over infinity. So we're going to use the same procedure. I want this highest power of x in the denominator to go away. Right? Which means that I need to come in with what? 1 over x squared, right? 1 over x squared, and I need to do that on the top and the bottom. But there's a problem. The problem is that this is a square root. And so if you put something out here, right, you can't just, right, the square root like has an impact on things. So there's like 3 or 4 different ways to teach this. Here's the way I like to teach it. I want you to just think about something. Let's go back in college algebra for a second. If I write the square root of x cubed, I hope that we're all comfortable with the idea that that's the square root of x squared times x. And that for every pair of factors like this, I can pull this out as an x, but I'd still have the x left inside. Yeah? Because this is x squared pull that out, I've got an x out here and then square root of x. So these mean the same thing, right? Any questions on that? Another way to look at this, and the way I want you to look at it right now, is that, yeah, of course, if I start from here, you should be able to get to here. But what if I ask you to go from here to here? What you do is you have to push this x back in, right? And because it's a square root, when you push it back in, what happens to it? It gets squared on the way in, you see? The x that's out here, to push it into the root, it has to get squared. So what I need to be thinking about is, what do I put out here so that when I push it in, it becomes a 1 over x squared? A 1 over x. I need a 1 over x on the outside. And then on top, I need a 1 over x as well. And again, the idea is that I need to kill off x squared. So I need a 1 over x squared, but it has to start on the outside of the root. So when it comes in, it becomes squared. When you square 1 over x squared, when you square 1 over x, you get 1 over x squared, right? 1 over x squared, you square the top, you square the bottom. Any questions on why I'm using 1 over x? All right, let's distribute through here. On the top, here to here, the x's cancel. I'm just left with the 5. And then here to here, I just get plus 1 over x. On the bottom, I have the square root. I pushed that 1 over x inside. It became 1 over x squared. And now I still have to push that through the denominator, what was underneath the root, right? That one went through. This one went in and got squared, but now I still have to pass it through those two. Next line, limit x goes to 0. I'm sorry, x goes to infinity. 5 plus 1 over x over the square root of 4x squared over x squared, which is just 4, right? And then plus x over x squared, which is just 1 over x. And then when I take the limit, it will go to 0, right? Here, 4. Here, x over x squared is just 1 over x. Now take the limit. Anything that's a fixed number over x is going to go away, isn't it? That's going to go to 0, right? That's going to go to 0. And so what am I left with? 5 over 2. 5 over the square root of 4, right? Which is going to be 5 over 2. 5 halves.